Hello, I'm Professor Steve Miller. Let's talk about the Cebeci and Smith turbulence model. It's an algebraic model published in 1974. It has had incredible popularity for a long time and is particularly created for boundary layers. Let's look at the major equations here and how they work. This particular model is a split model in that it contains an inner and outer region of the boundary layer and are modeled separately, but the equations must connect seamlessly in between. The inner layer contains the viscous sublayer, the buffer layer, and inertial sublayer of the model. Let's look at this split, and it's split in terms of the eddy viscosity nu sub t, which recall we talked about in previous lectures. In the inner part, we'll define an eddy viscosity, and it's a model. Remember, we need to close the equations. It's an algebraic model, so it consists of algebraic closed form equations, though they might contain differential or calculus within them. Let's look at the first one for the inner eddy viscosity. Cebeci and Smith proposed nu sub t I, so sub I for inner, is equal to the length scale squared, times the magnitude of partial u, partial y, right? That's the derivative of the velocity in the streamwise direction with respect to y, the distance from the wall, times gamma. And we'll talk about gamma in a few minutes. But you'll note that it's the intermittency factor, and I is for inner. This is one of the most important equations and represents the part of the closure for the inner part of the boundary layer. Remember, the boundary layer has direction x and distance y from the wall, and it has some particular profile u, which we want to penalize or modify with an eddy viscosity. Now, we'll call this equation 28, and if you are keen, you would have seen that this is actually a form of Prandtl's mixing length model with a modification. And this modification is L equals ky times 1 minus exp of negative y plus, all divided by a plus. And this is a bit empirical, but we'll define and tell you about these portions of the equations just in a second. For those of you who've had a turbulence class, you know that you can plot the boundary layer profile as a function of y plus and u plus to try and collapse portions of the profile. And when we plot boundary layers, there's the inner viscous sublayer here. There's a log layer and the outer area, which contains Cole's wake factor usually. You should review this if you don't understand this concept. But nonetheless, this very first part of the term here is Prandtl's mixing length hypothesis, or length model, where k is a constant and y is the distance to the wall. Y plus is in non-dimensional coordinates, and so is a plus in the inner coordinate system. Here, let's define, if you don't remember what y plus is, y plus equals y, which is just the normal coordinate, times u sub tau all over nu, which is the viscosity. U tau we call typically the friction velocity, and it's equal to the square root of tau at the wall divided by rho at the wall. Here tau is the wall shear stress and density is the density at the wall. Sometimes we might rho sub w because it's specified density at the wall, but it's a constant in this formulation due to incompressibility. Shear stress at the wall is tau sub w, and of course that is equal to mu, the viscosity, times partial u, partial y, at the wall, which we just say is w. So now we have these defined, and they can always be used to collapse your boundary layer and inner coordinates. Now we're going to say there's a so-called Van Driest damping function. That's the last part, of course, of equation 29 right here, which we defined with y plus just now. But we still need a plus. The so-called Van Driest damping function is a plus equals a u tau all over nu, viscosity. And you can see it only depends on the streamwise pressure gradient according to the following equation. 26 all over the square root of 1 minus 11.8 times P plus. We'll say that this equation is 30. Here P plus is a dimensionless pressure gradient, nu of u, and I'll mention this particular formula u in a second, divided by u cubed of tau, which we just described a few equations ago, times the derivative of du dx. Here, u is basically the velocity outside or at the edge of the boundary layer. Mind you, it's turbulent. Okay. We'll also note I introduced this part of the equation in the inner part as gamma. Let's look at gamma now. Gamma is the so-called intermittency factor. And this, of course, accounts for the fact that the turbulent boundary layers are not just some steady motion, but there's some large intermittency of the eddies at the outside of the boundary layer. And this isn't as intermittent, of course, near the wall, where there's becoming a viscous sublayer, which looks like very close to laminar, until especially very, very close to the wall. So this means that the boundary layer is that is intermittent or very chaotic, on and off, if you will, gamma amount of time. So it's like a fraction. Let's look at a particular form that's proposed. One fellow named Klebanov has shown experimentally for these low-speed attached zero-pressure gradient boundary layers that gamma should go as something like 1 plus 5.5 times y over delta to the 6th power, all to the negative 1. So you can see as y goes to 0, like we go towards the wall, this whole thing goes as 1 over 1. So gamma would be 1 at the wall. As y becomes large, of course, this second term becomes larger, and we get a fraction. It'd be 1 plus a number greater than 1. This value here, of course, can't become larger than 1 by definition, and it'll be about 1 plus 5.5. So for a distance a long way from the wall, it'll be about 1 over 6.5. So you'll see now, let's just define delta just to close up the function. So delta is the y position where u over u is equal to 0.995 by definition. Remember, u is roughly the free stream velocity. So you can see we get about 1 at the wall and a much smaller fraction far away from the wall for the intermittency. We haven't talked about the eddy viscosity in the outer part of the boundary layer. Remember, this is only the eddy viscosity in the inner part of the boundary layer. So we have to find another eddy viscosity, which we'll define now. Whoops, and I want to mention that I'll call this equation 31, and I think I should label a plus as 30. I did that already. Sorry about that. Let's define the outer viscosity. Nu sub t, O, so eddy viscosity, which is sub t, and outer, O. We'll say Cebeci-Smith wrote that alpha u of delta sup star times gamma, the same intermittency factor as before. What does this equation mean, 32? This means that in the outer layer, the characteristic velocity will be proportional to the outer edge velocity, right here, with an alpha of a constant usually, or some function. And Cebeci-Smith used a function which we'll introduce in a second. Whereas the characteristic length scale will be proportional to the displacement thickness. And this is from boundary layer theory. This is the displacement thickness, and it's a well-known definition of the integration from the wall to infinity of 1 minus u over the ambient velocity times dy. The function alpha is dependent on the so-called local Reynolds number within the flow based on the momentum thickness. And we need to define, of course, momentum thickness also. So theta will be integration from 0 to infinity of u over u times 1 minus u over u dy. Here, Cebeci and Smith proposed alpha as 0.0168 times 1.55 all over 1 plus capital pi. Pi, of course, is a factor. I am going to label, I decide alpha should be its own equation too. 33 because it's so important. But what is pi? Pi will be equal to 0.55, and this isn't little pi, of course, which is 3.14, 159, etc. Nope, this is capital pi. 0.55 times 1 minus exp of negative 0.243 times the square root of z1 minus 0.9, minus 0.298 z1. Now close up these brackets. Notice the exponential goes across these to this parenthesis set. And z1 is just another coordinate with respect to y, and it's equal to the max value, which is easily programmed in Fortran, your favorite computer program, of 1, or re theta, which is the Reynolds number based on displacement thickness theta. Momentum thickness theta. Remember, this is momentum thickness. And this is displacement thickness. Anyway, our re theta 425 minus 1. For some of the insight behind some of these terms, you're going to have to go back and read the original paper of Cebeci and Smith. It's the best way to learn the material. Nonetheless, we've closed a model which is algebraic, extremely computationally efficient for turbulent boundary layers. You'll see that indeed the switch between the inner turbulent viscosity and outer turbulent viscosity indeed is at a position y where both values are equal to each other. So only one position, y, will have nu ti equal to nu to. And so the model's closed. And you can find this particular model in many contemporary CFD solvers. Thank you very much for your time today. I'm Professor Steve Miller.